Hello! So far in our strategic games, a player's choice involves choosing one strategy from a set of strategies. We now consider another way of choosing a strategy. Instead of choosing one strategy, a player sets a probability distribution among all possible strategies and picks their actions probabilistically. We briefly talked about rock, paper, scissors before, where playing a strategy at random is a better choice. We will look at a simplified version of it in the game of matching pennies. In this game, two players each has a penny. They simultaneously show heads or tails. If they match, then player 1 gains the penny from player 2. If they don't match, then player 2 gets the penny from player 1. And here is the payoff table for this game. You can quickly check that there is no Nash equilibrium in this game, at least not in the way that Nash equilibrium has been described so far. So now let's allow players to play this probabilistically. For example, player 1 might play heads 1/3 of the time and plays tail 2/3 of the time, and player 2 might play 3/4 on heads and 1/4 on tails. Now when we talk about Nash equilibrium, we're looking for a steady state. That is, no player wants to change their strategy. So could there be an equilibrium here? If player 1 plays 1/3 heads and 2/3 tail, then player 2 wants to play heads more often than tails, so they don't match more often. But if player 2 wants to play heads more often than tails, then player 1 wants to play heads more often than tails so that they match more often. And then player 2 wants to play tails more often than heads, etc. etc. So it seems that it is stable only if both players play heads and tails with equal probability. And that's what we might expect to happen in such a game. We now give some definitions and notations. A mixed strategy for player I is a vector xi, which are non-negative real numbers indexed on the strategies for player I, such that the sum of all the numbers over all strategies for player I is 1. This is the probability distribution over the strategies of player 1. The set of all mixed strategies for player I is denoted by delta with superscript I. A mixed strategy profile is a vector x with n entries, where each entry xi is a mixed strategy for player I. The set of all mixed strategy profiles is denoted by delta, which is the Cartesian product of delta 1 to delta n. The mixed strategy profile with player I removed is x minus I, which is in delta minus I. A couple of notes here. If we play a strategy with probability 1, then it is called a pure strategy. This is the way we play games before this lecture. Also, as convention for this course, we will use S's to represent pure strategies and X's to represent mixed strategies. In our example of matching pennies, if we order the pure strategies in the order of heads and tails, then we had x1 is xh1, xt1, which is 1/3, 2/3, and x2, which is xh2, xt2, is 3/4, 1/4 as mixed strategies. The strategy profile is then x, which is equal to x1, x2, which is equal to this. Now you may be wondering, what does playing a mixed strategy mean practically? There are a few interpretations, and different game theorists will give you different interpretations for mixed strategies. We will quickly go over two of them. One way of thinking about mixed strategies is it introduces unpredictability in games that are played repeatedly. For example, in sports, you want to be unpredictable in the way you play. Like in a penalty kick situation, you do not always want to kick to the same side. Or, in politics, you do not always want to make major announcements on Tuesdays. Then the opposition can preempt you by making their announcements on the Monday. Alternatively, you can think of a player as representing a population, with probability of a strategy being proportional to the portion of the population who prefer it. For example, say 55% of the population like donkeys and 45% like elephants. Then the mixed strategy 0.55, 0.45 represents what we would expect to happen in an event. Say perhaps there will be more donkeys in zoos. Now we gave a vague idea of how mixed strategies might be played in matching pennies, but we want a more formal way of defining what is the utility of the players given a strategy profile. One natural idea is to use the expected value as the utility. The notation for utility is going to be a bit dense, so we will illustrate with an example first. In our matching pennies example with these probabilities, let's consider the utility of player 1. There are two cases. If player 1 plays heads as a pure strategy, then looking at player 2's distribution, there is a 3/4 chance that they will play heads, in which case we get utility 1, and 1/4 chance that they will play tails, in which case we get utility -1. So the utility we expect to get for playing heads is 3/4 times 1 plus 1/4 times -1, which is 1/2. Similarly, if player 1 plays tails as a pure strategy, then there is a 3/4 chance we get -1 and 1/4 chance we get 1, and we expect to get a utility of -1/2. And these are what we expect to get if player 1 plays heads or tails as a pure strategy. But player 1 plays heads 1/3 of the time and tails 2/3 of the time. So we would expect to get a utility of 1/2 1/3 of the time, and a utility of -1/2 2/3 of the time. So the overall expected utility is 1/3 times 1/2 plus 2/3 times -1/2, which is -1/6. We now write down the definition of the utility. We are given a strategy profile X in delta. The expected utility of a pure strategy Si for player I is Ui of Si x minus I, which is the sum over all strategy profiles of the other players, this expression here. The first part is the utility of playing Si as a pure strategy. The second part is the probability that the remaining players do play this strategy profile S minus I. Note that Ui of Si S minus I is the utility from the pure strategy game. So this is the expected utility of playing a particular pure strategy Si. So then the expected utility of player I in the strategy profile X is the sum over all pure strategies of player I, this expression here. The first part is the probability that player I plays the strategy Si, and the second part is the utility that player I gets for playing Si. Using our notations for matching pennies above, we see that U1 of H x2 is 1/2. U1 of T x2 is -1/2, and U1 of X is -1/6. We now look at a different example. Suppose 3 players each make a choice between A and B. A $1 prize is split among players who pick the majority choice. Suppose that x1 is p1 minus p, x2 is 1/2 1/2, and x3 is 2/5 3/5. What is the expected utility for player 1? We first look at when player 1 plays A. There are 4 cases depending on what the other 2 players have played. In the first case, the utility of AAA is 1/3. That's because all 3 of them played the majority choice, so we split the $1 3 ways. The probability that this happens is the probability that player 2 picks A times the probability that player 3 picks A. And this is 1/5. In the second case, the utility of AAB is 1/2, as only 2 people have chosen the majority A. The probability that this happens is when player 2 picks A and when player 3 picks B, and that's 3/10. For the case of ABA, the utility is 1/2, and the probability that this happens is 1/5. And in the case of ABB, player 1 did not choose the majority, so the utility is 0. And it does not matter what the probability that this happens is, it's going to be multiplied by 0. So the utility for playing A is u1 of A x minus 1, which is 1/5 times 1/3 plus 3/10 times 1/2 plus 1/5 times 1/2 plus 0. And that is 19/60. And you can check on your own that the utility for playing B is 7/20. So the expected utility for player 1 is u1 of x, which is equal to p times 19/60 plus 1 minus p times 7/20. And that's equal to 7/20 minus 1/15 p. Now it would make sense to pick p is equal to 0. Can you see why? So player 1 would play B as a pure strategy. And we see that this is because player 3 is more likely to pick B, letting us form a majority more often. And that is our introduction to mixed strategies. In the next lecture, we will look at mixed Nash equilibrium.